Welcome back, guys. In this video, we're going to talk about binomial expansion, and we're going to use something called Yang Hui's triangle. When I was in school, they called it Pascal's triangle, and I believe in Italy they also call it Tartaglia's triangle. They are referred to the same thing. You can call it whatever you want, but I just wanted to give recognition to other contributors. I believe Yang Hui used it before Pascal, so that's why I decided to call it Yang Hui's triangle. But keep in mind that they all refer to the same thing. So the way you use this triangle is that it's used as the coefficients for binomial expansions. As you can see right here, the zero, it refers to the zeroth row. Number one refers to the first row and second row and so on and so on and so on. So what that means is that if you have a binomial, which is the sum or difference of two unlike terms. So let's say we have the terms A and C, and you add them. Because they are two terms, a two-term polynomial, it's called a binomial because it has two terms. Similarly, if you have three terms, guess what it's called? Not a binomial, a trinomial, right? And it just keeps going. But it's a type of polynomial. So what the Pascal triangle lets us do is that if we expand a binomial, you actually use these coefficients. And I'll show you. Here's an example. Let's say I have, like my example, a plus b squared. So those of you probably know something called the FOIL method. So a plus b squared is the same thing as a plus b quantity multiplied by a plus b. So the way you do that is you use something called the FOIL method. FOIL. So F stands for first. So the first terms, in this case, it's a and a. So a times a gives you a squared. O means outer. So the outer terms, in this case, a and b. So you get a b because a times b is ab. And we're adding plus and plus, so we get a plus in the middle right here. Plus the next term, I stands for inner. So our inner terms are b and a, which is the same thing as AB. So B times A is the same thing as A times B, so we get AB again. Okay? Multiplication is commutative. You can swap the order. And L means last. So B times B is B squared. B squared. How is this related to the triangle? Well, we had an exponent of 2, which means we're going to look at the second row right here. The second row. All right? Remember, the first row, even though it's the first row, we call that the zeroth row, the zeroth, all right? And I'll explain why in a bit. But first, let's keep going with this one. So we have a squared plus, well, we have 2ab. So we have 2ab. Let me use a different color for the coefficients. Let's go with orange. So 2ab plus b squared. But there's no coefficients on a squared and b squared terms. Well, there are. It's just a 1 in disguise because we have one a squared term and we have one b squared term. Now, if you look at the second row, you can see that the orange terms match the numbers on the second row, 1 to 1. Look at that. That's why this triangle is useful because it keeps track of the terms for us. Okay? So this is a quick way to multiply binomials because past the second power, even the third power, past the third power, it gets really hard to keep track of all the multiplication. So this is why we use Yang Hui's triangle. So let's do an example. All right, let's do an example. So we're going to do x plus y to the fourth power. So that's going to be x plus y, quantity, times the quantity x plus y, times the quantity x plus y, times the quantity x plus y. If you want to multiply this out the old-fashioned way, be my guest. But I'm telling you right now, it's going to be very, very difficult. This is how you do it, using Yang Hui's triangle. So I notice first that I'm looking at the 4. So I'm going to go to the fourth row on my triangle, and we're going to use that. So fourth row is this one right here. Right there. Okay? You might ask yourself, well, what if the rows weren't numbered? Well, okay, watch this. They're not numbered anymore. So how do you know which one's which? Well, you look at this one right here. You see that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those numbers right there on that diagonal line, they tell you which row you're going to use. So if they were numbered and I'm using the fourth row, I just look for the 4. There it is. So I'm going to use this row of coefficients right there. Okay? So let's just put everything back for simplicity. All right, we're using that right there. Cool, cool, cool. This is how we're going to do it. We're going to take x and y. X and y. All right? And we're going to take the 4 and put it on the x right there. Just like that. And now the exponent for the y will be a number that plus 4 makes 4. So 4 plus what makes 4? Well, 0. Right? 0. So now we're going to add again x and y. Instead of 4 this time, we're going to drop it down by 1. So now it's 3. 3 plus what makes 4? Well, 1. So that's the exponent for the y. And we keep going. X and y. Notice that I'm taking the terms inside the binomial and multiplying them with each other. Okay, so we're at 4, 3. Well, this time it's going to be 2. And 2 plus what is 4? 2. Keep going. Plus x and y. Well, it's 3. So 4, 3, 2. Well, this time is 1. And 1 plus what? 1 plus what is 4? Well, 3. And let's keep going. Maybe I can decrease the thickness on the pen. Yeah, let's go with 2. Plus x and y. And this time it's we're dropping the 1 down, so we have a 0 and a 4. We can stop there. But we're not done. We need the coefficients now. So, and it's in order. So we start with a 1. So it's a 1 right there. The next one's a 4. So it's a 4 right there. The next one's a 6. 6 right there. The next one's a 4. 4 right there. The last one is a 1. A 1 right there. Look at that. But we can simplify this even further because there's a rule of exponents for any number x raised to the 0 power is equal to 1. But there's a caveat. X cannot equal to 0 because 0 to the 0 power is it's undefined or indeterminate. So we can't do that. So now y to the 0 power is 1. So we're going to simplify this. So 1 times x to the 4th times 1. Well, that's just x to the 4th. Plus, now we can keep going. 4 x cubed and y. When the exponent is 1, you can just leave it as the term. So y to the first power is just equal to y. Plus 6x squared y squared plus 4x y cubed plus 1, I'm sorry, plus y to the fourth power. And that's the expansion of the binomial. Cool, cool, cool. Let's do another exercise. This time we're gonna pick a different one. Let's go with oh, I know. B plus a letter P to the sixth power. B plus B raised to the sixth power. So we don't know which row that is, but it's not numbered. Well, we know the exponent is a 6, which means we got to find the 6 on the diagonal, which is right here. So we're going to be using this row right there. Cool? Cool. All right. So let me just highlight that because I need to know it. Boom. All right, perfect. So now let's start expanding this bad boy. Well, first, I'm going to write my terms like this. B, P. Since the exponent is a 6, the B gets a 6 and the P gets a 0. Plus B, and we knock it down by 1, so 6, 5, which means the P gets a 1. Plus B, 4, which means the P gets a 2. Remember, the exponents add up to the power that we're raising the binomial to, okay? So keep that in mind whenever you're expanding. Plus BP, 4, 3, and 3, right there. So B cubed, P cubed. Plus BP, 2, 4. Plus BP, 1, 5. Plus BP, 0, and 6. Cool. Let me give myself some more space. Right here is fine. Awesome. Now we have to put in the coefficients on the front of each term. Cool. So we start with a 1. So we have a 1. Then a 6 right there. Then a 15. Oh, wow. Right there. Then a 20. Then a 15 again. Then a 6. Then a 1. Boom. Now let's simplify the powers of zeros and ones so that we can make the expression look nicer. So 1, b to the 6, p to the 0 is just b to the 6 plus 6 b to the 5th power p. Gotta make sure my b's don't look like 6's. Let me do a better job. All right, let's keep going. Plus 15 b to the 4th p squared plus 20 b cubed p cubed plus 15 b squared p to the 4th plus 6b p to the 5th plus p to the 6th. And this right here is our binomial expansion. Pretty cool, huh? Now, just as a little exercise, you can construct your own Pascal's triangle. Okay, and this is how you do it. Notice that the numbers add up to the one below it. Look at that. 1 plus 1 is 2. 2 plus 1 is 3. 1 plus 6 is 7. 35 plus 35 is 70. 7 plus 1 is 8. 84 plus 126 is 210. So that's how you make it. So what do you guys think? And notice that there's always ones all the way across. So we're going to put a 1 right here. Let's make our own Pascal's triangle. The next row. Which power would that be? So the 10th. So the next one would be 11. So 1. 1 plus 10. 11. 10 plus 45. 55. 45 plus 120. 165. And it keeps going. 120 plus 210. 330. And then 210 plus 254. 252, I'm sorry. 462. And then 252 plus 210. Again, 462. And then 210 plus 120. 330. Notice that they're repeating again. Look at that. It's a little pattern. It grows, and grows, and then you get the same numbers again. So you only really have to add once. So the next one, 330, well, before 330, so it's 165. And then it's going to be 55. And then 11. And then a 1. Don't forget the 1 in the end. And that's how you keep building Pascal's triangle. So I hope this video was helpful, guys. And I'll see you guys on the next one.